The laws of Galilean relativity are fairly straightforward in one dimension. The velocity of the boat relative to the ground, what we observe from the shore, is going to be the velocity of the boat relative to the water. That's what the engine is doing, plus whatever additional motion the current is providing, the velocity of the water relative to the ground. Look at the way the water cancels out. Boat to water, water to ground gives you boat to ground. In this class, we can use the slightly shorter ground velocity equals engine velocity as set by the pilot plus whatever the current is doing. In this case, if the pilot is trying to drive this boat at 15 meters per second east, notice we have to use bracket notation because this is a two-dimensional problem, and the current is flowing west against the boat at 4 meters per second west, that is -4 east, you'll notice the boat will have a very hard time coming through, and relative to the ground, it's only going to be going 11 meters per second or so to the east. And if you want to express that without the brackets like a normal person, maybe it'll look prettier. Now, let's try this in a two-dimensional problem. This is the classic river crossing problem. If you're trying to get straight across the river with the current going, what angle do you need to navigate at to make sure you can get across the river where you want to land? Let's start with a nice right triangle just to prove the point. Here's the river with the velocity of the current sweeping the boat along this way. Let's say 5 meters per second just to prove the point. We'll say 5.0 meters per second if we want a second sig fig. Let's say you've got a boat and you are trying to get that boat right across the river, straight across to the boathouse and the dock over here. If you aim right across the river, will you make it? Solve the problem and see. If you aim straight across the river with an engine velocity of 20 meters per second straight off your dashboard and your fuel gauge, where will you end up? Pause, press play to check your work. Pythagorean theorem, a nice right triangle, square root of 20 squared plus 5 squared ought to give you a hypotenuse of about 20.6 meters per second, a little over 21 meters per second squared. You'll get there early, but you'll be swept downstream at an angle of theta. And if downstream are a lot of nasty sharp rocks, that is not going to be good. How far are you going to be swept downstream? Well, let's find theta. We have opposite. We have adjacent. Theta is the arctangent. It is the angle whose tangent is 5, check, going east, positive, over 20, check, going north, positive. That's about 14 degrees. So our ground velocity, check, this is not east, this is north. This theta is touching a pink north, so that's going to be north, 14 degrees towards the east. That is your final bearing. You are going to be swept downstream and by 14 degrees all the way across. When are you going to get there? Are you going to be early or late? Well, let's try some kinematics. You have an initial velocity. Hey, you even have the current's initial velocity. You have, well, let's assume your engine stays off the whole time. If your engine stays off the whole time, you are not going to be accelerating. This is a vector. It has your displacement in the y direction, that's north that you want. It has your displacement in the x direction, that's east, that you don't want. We're going to write that in bracket form. Keep those separate and independent. Your velocity has two components. Interestingly enough, the x component is very clearly given. And the y component is very clearly given because we have this nice orthogonal problem So all we need to know is the width of the river. If the river was 350 meters across, then we have y. 350 meters across to the north equals 20 meters per second north times time. Solve. See how much time it's going to take you to cross the river, and that done, find how far downstream you're going to be swept in that time. Pause, solve, press play to check your work. It should take you 17.5 seconds to cross the river, and if you're going 5, like I said, I'd give you another sig fig, meters per second east for 17.5 seconds, then that should put you a whopping 87.5 meters downstream to the east. Well, you're lucky the rock started at 100 meters, but you don't want to be lucky. You want to be at the boathouse. This is the problem. We swept off course, and it's a very bad thing. Let's start this problem all over again and do a more realistic problem, a navigation problem, where you point the boat where you want it to go in order to get where we're going. Quick fact check. If you're due to be swept downstream to the east, which way should you point your boat? If you're going north and you accidentally end up going northeast, what should you add to the east to make it go away? Draw a new diagram. Check your diagram. We're drawing it in an entirely different sequence. Instead of simply pointing our boat straight across the river and hoping for the best, we are going to start with our resultant. Our final vector, VG, previously the final answer, is going to be over here. It's going to be straight across in the northern direction. Now, the answer to your previous question, what plus northeast equals north? The answer is, of course, is west. Northeast plus west is north plus east, west plus west, that's north. That means you need to turn your boat toward the north. You need to navigate this way so that when the current sweeps you that way, it sweeps you on course rather than off course. This theta is no longer the theta at which you're swept downstream. This theta is the theta that you, as the engineer, point your boat, not what people on the ground observe when they have to come and rescue you and tow your boat back to the boathouse. This is the answer we're looking for. True or false? Since the river swept your boat 14 degrees downstream, you should just go 14 degrees upstream and be done. Label the sides on your right triangle, indicate true or false. Press play to check your work. If you got massively, massively false, you've got a correct diagram. Check it out. This side of the right triangle is 5, but 20, which used to be one of the legs of the triangle, is now the hypotenuse. This was a 5, 20, 21-ish triangle. This is now a 5, 20, something significantly less than 20 triangle. These are not similar triangles, gang. The problems are not similar. If you're making a course correction, you have to correct for what should be, not take the angle that shouldn't be and try to work against it. Start this problem from scratch. Solve for theta whichever way you can. Press play to check your work. Well, they were close. I'll grant you they're close. If anything you did gave you an angle of 14.5 degrees, you're good to go. If, to get your theta, you used your trusty arctangent function with a ground speed of just under 20 meters per second, 19.4. Why? Because you're fighting the current. The current is slowing you down. Then you're in good shape as well. You may arrive a little bit longer than the whole 17.5 seconds it took you to be swept downstream, but you'll arrive straight across to the boathouse, assuming, check your bearings, that you navigate at north 14.5-ish degrees. I know we should be rounding down to 14 degrees again, but I want to prove a point about the angles not being the same, toward the west. Moral of the story, 5 meters per second is not precise data. Get an anemometer to measure the wind speed, or look up the current speed as measured by your local Coast Guard to get seriously more than 1 sig fig in the 5 meters per second, assuming you want to hit the dock straight on and don't want to be off by a meter or two. Let's do the more general problem, laying aside our critical assumption that everything in life always travels in straight lines. Let's do this for an airplane that wants to fly directly northeast. Remember, northeast is an exact 45-degree angle here, so we've been given a gift of an infinite number of significant figures. Once we're no longer going across, we're going to need to drawing little baby coordinate axes everywhere we go. If we say we want this plane to actually fly northeast, we jolly well better make sure it's flying northeast. This is where our big rule from the beginning of the unit comes in. All angles have to be measured from the x-axis in order to use these formulas. So here is our theta g. We are aiming for 45 degrees. This is VG. VG is our ground speed. If you think you know your ground speed in the problem, think again. The ground speed is what air traffic control measures. If you knew your ground speed, you would be telekinetic, you could fight against the wind, air traffic controllers would not have jobs, and you would probably be Superman or Wonder Woman and probably be working on peace on Earth rather than trying to point your plane into the wind. What you know is the air current, and air currents never flow straight east. Yeah, remember turbulence from air resistance? This is like that, only we're pretending it's simpler. What if the prevailing air current is going northwesterly, like this? Of course, they won't tell you that it's going northwesterly. They won't tell you that it's going southeasterly. They'll say, and you'll hear this on the radio, winds coming out of the. If a wind is coming out of the northwest, it's really going southeast. So you need to take the current speed that they give you. If they say winds coming out of the northwest, or if you translate that into an actual math class angle, winds blowing at east 71 degrees south, that's going to look like this. Again, it doesn't make a whole lot of sense until we draw the little baby coordinate axis for each vector. Notice we are not doing this problem in official math class order. Our final diagram is going to have to be tip to tail vector addition, but we can't do vector addition because what we're looking for is not necessarily the resultant here. Here is our VC, and the angle made by the prevailing current is here. There is your east 71 degrees south, or whatever it is. We can't do this in our head anymore. It's real easy to say northeast plus west equals north, but we are going to need some real trig here. Now, if the wind pushes you this way into the path that you want to go, where do you have to point your plane in order to get here in time for the wind to get you where you're going? There. This is your VE. This is your engine speed. This is the one that you know. You will probably have great difficulty making this to scale. That's okay. Use pencil, erase, redraw several times. VE, the angle at which you want to navigate, is this one here. It goes all the way across. It is clearly bigger than the 45 degrees you wanted to go because winds blowing southeasterly means that you're okay with the east. East helps, but you need to go more north than you planned to so that the southeasterly winds will take you where you want to go. Now, set up your vectors in bracket form. Don't even try to do this in Cartesian coordinates. I'm going to suggest that you set up your Galilean relativity equation vertically like this. Engine velocity, you know it. What you want to know is which direction it should be. Current velocity, you know both speed and direction. It is the problem. This is the solution. Ground velocity, you don't know the ground speed, but you do know the direction you want to go in. This is VG, you don't know it. Cosine theta g, that's the direction you want to go in. And the other component, the y component, is sine theta g. This is the formula I said you could not use unless you very carefully in this picture measured all angles from the x-axis. This northeasterly, that's east 45 degrees north. This southeasterly, that's east 71 degrees south. This angle here is in the first quadrant. This is a nice problem. Your calculator will give you the answer. If you ended up having to point the plane west, just like last time, you're going to get a reference angle over here. You're going to have to do a quadrant check, factor in that extra factor of 180 to make sure your angle here in the second quadrant or here in the third quadrant is going in the right direction. Important notes and reminders. This is the one you typically know in the most realistic problems. If you didn't know where you want to go, you wouldn't be doing a course correction. You would be doing a hisbodedus in the woods, being at one with nature, only on a plane in the air. This is your ground speed. Typically, you do not know this. If you think you know this, check the problem. Check your reading really carefully because I'm betting you're mistaking it for another number. If you have a number in here, be very, very suspicious because I think you're being over-optimistic and you're using the engine speed, which is typically given. It's never more than 170 meters per second for a single engine propeller plane. That's going to be 170 cosine, the angle you want to go at, and 170 sine, the angle you want to go that. This is the speed you know because it comes off the speedometer on your dashboard. The speed of your plane relative to the air, what your plane is doing on its own. When you're finding vector components, be sure that the magnitude you have goes up here. This is typically the number that you know. Oh, well, this is also a number that you know. If you didn't know the prevailing currents, you've got no business getting in the plane. You know the wind speed, you know the wind direction. The only thing you have to be really careful is to make sure that this direction is measured relative to the x-axis or from the east. You got to do this in all cases, but this is the number you typically have to look at because it's given in the problem. You know this too. Oh, Mrs. Eliezer, couldn't we do all of this just using the law of sines? Yes, you could. If you see your way clear once you've drawn the triangle over here to using the law of sines, answer the question using the law of sines. If you see your way clear using the law of cosines, do that too. The advantage to this setup, which is slightly more time consuming to set up, is that you have every one of the 6 pieces of information in its place. You can find navigation direction, you can find ground speed, you can find quantities relative to other quantities, and all of the angles given are going to be measured from the positive x-axis, ready to use in other formulas. This is the setup I recommend for problem number 2 on the Galilean Relativity sheet, the single hardest problem I can possibly throw at you, where none of these numbers are cardinal angles. If you can do number 2, you can do anything in Galilean Relativity. Number 2 is a tough cookie because it has 2 unknowns, and nothing nice ever equals anything else. But note here, you have 2 equations, one here with the cosines and one here with the sines. If anything is a cardinal angle, for instance, if you want to fly north, then this component is going to be 0. You don't need to write VG cosine theta g. You can see ground speed is north. That is fully in the y. Go that way. That means this equals 0. That means you just put a box around this equation. You have 170 cosine theta plus some nasty number you already have. It's a decimal, equals 0. Beautiful. Solve for theta. In the one case where nothing equals 0 and you can't pick the easy side to work on, there is one thing you can do. Write up the sine equation. Trust me on this. Start on the right. Write it directly over the cosine equation. Try it now. Press play to check your work. Did you write it down? All right. No. This we know. This we don't. This is a decimal. This is a decimal. This we don't know. This we do. Watch. Can do that. We can divide one equation by another. Sure. We've been adding and subtracting and multiplying them for ages. Let's try dividing. Watch this. Look at the right side. Simplify. What does that simplify to? Remember, theta g is something we know. Can you find it on your calculator? Because if you can use your CAS to solve this horrible thing that is now equal to something very small, very short, and very simple. Now, you only have one unknown. You can use the n solver. If you don't have CAS, shove this into your calculator and let it do the answer. If you don't like using the solver, graph. Make a line where y1 equals, hey, what's sine over cosine? And y2 equals this nasty mess, and scroll up till they intersect. We now pause in the memory of all the honors physics students who memorized this equation, studied nothing else, put it down on the test, and then found that the test asked them for ground speed and wanted to know when the plane would land and whether you would be early and needed a gate change, or whether you would be late and the company needed to pay off the passengers with vouchers for restaurants. Don't memorize this equation. Learn the process and use this equation when you need it so you can do the course correction or the estimated time. Better still, you can be the programmer who works for Orbitz, who makes the software that gives the pilots the course corrections and gives the flight agents and the people at the tower your estimated time of arrival. Pull in excellent money as a programmer and pay off your student loans.